So what we're going to be talking about is some of the fundamental concepts behind thermochemistry. So let's first look at some definitions. If I look at thermodynamics, well, thermo means heat, dynamic, if something's dynamic, it's changing. So with thermodynamics, it's going to be a study of how heat is transferred, how heat is changed from one thing to another. With thermochemistry, it's going to be dealing with that heat exchange, dealing with chemical reactions and how we actually get heat out of chemical reactions, or we absorb heat in chemical reactions. The fundamental premise behind thermodynamics is going to be that when energy is transferred from one thing to another, it's going to appear as work or heat. Okay, so let's look at an example of thermochemistry. So I'm going to mix some chemicals together. I'm going to take potassium chlorate. I'm going to take sugar, and I'm going to take sulfuric acid, and this is going to be concentrated sulfuric acid. What I'm going to do is mix the potassium chlorate and the sugar together. That's that white powder there. And then what I'm going to do is add a couple of drops of the concentrated sulfuric acid. And let's see what happens. Okay, that's an example of an exothermic reaction. You can see that there was heat produced there. Okay, we could see the flames coming out. That's thermochemistry. We take a chemical reaction, we're getting this heat exchange. Okay, and in this case, we produced heat, we got those flames out. So we're going to talk about that a little bit more. All right, some additional concepts we need to get down is going to be dealing with energy. Okay, really, when we talk about this heat and work, it's going to be dealing with forms of energy. Okay, so we have to worry about potential energy. Well, potential energy is the capacity to do work. That's the typical definition of it. Okay, a lot of times when we think about potential energy, we're going to talk about chemical potential energy. All right, and that's going to be the energy obtained from these chemical reactions. Okay, so these chemicals, when mixed together, they have a potential to produce energy. We can also have kinetic energy, which is the energy associated with motion. Now, in a chemical reaction, motion is going to be related to thermal energy, how those molecules are vibrating, how they're moving. Let's look at a picture of this. If I look at potential energy, if I start with a more stable state, for example, let's say I have a negative ion and a positive ion, and those two are combined together, that's a stable state, like sodium chloride, table salt. Okay, it's stable in its solid form when they're combined together. If I want to change it to a less stable state, I need to increase energy and separate those ions apart. Okay, well now if I have those separate ions, especially in the gas phase, they're at a higher potential energy, they're going to be more stable at a lower potential energy, so chances are they'll come back together, reform the salt, and release that energy. Okay, something else you could think of, if you think about gasoline you're putting in your car. Gasoline is volatile, it's flammable, it's in a less stable state. When you put it in your car, it goes into your engine, it combusts, produces heat, produces energy, comes out as exhaust. Well, the exhaust is going to be more stable. So I go from that higher energy state, the gasoline, which has potential energy, it has the potential to do work, to the exhaust, which is at a more stable state, a lower energy, and that exhaust is definitely less reactive. Now let's talk about work. Well, work is going to be defined as force times distance is one form of work. So if I take an object, I apply a force, I move it a certain distance, that's work being done on that object. Another form of work is negative P delta V, okay, pressure times the change in volume. All right, this is how things work in your car, where you have a piston, you get that gasoline inside the piston, it ignites, it forces that piston up, creates a pressure to do that, it changes the volume occupied by that piston. That's the work being done. So for this topic, we're not going to focus so much on the work, but we have to recognize that we can get work out of a system. Okay, we're going to focus more on heat. Right now, heat, when we think about heat, when we think about something being hot or cold, so the reason why something feels hot is because we get a heat transfer from the object to, let's say, your hand that you're touching it with. So if you put your hand on a hot pan, pan is hot, transfers energy to your hand, it feels hot to you. What about cold? Well, when you put your hand on a cold object, heat from your hand gets transferred to the cold object. That's why it feels cold. All right, so when we think about this heat and when we think about hot and cold is really energy transfers. Okay, it's this energy transfer of heat. Okay, and heat is going to be related a lot of times to this thermal energy. Okay, so how fast these molecules are vibrating or moving around. Now, when we look at this picture again of the gasoline and the exhaust, we can also, as we go from the gasoline to the exhaust, we definitely get heat out, right? Because that exhaust is going to be hot. We can also get work out. That's what makes the car go. So as we're driving around, we're getting work out of that reaction, that combustion reaction of taking gasoline to exhaust. We're also getting heat out. Okay, so both of those things are coming from that gasoline going to the exhaust. Now, an important law that we're going to deal with is the first law of thermodynamics, which is going to state that the change in internal energy of the universe is going to be equal to the change in energy of a system plus change in energy of the surroundings. In other words, energy is conserved. Okay, we're neither going to create nor destroy energy, it's just transferring energy around. Now, when we think about the SI unit for energy, we're going to be dealing with joules. So you have to recognize joules, and we represent that with a capital J. And keep in mind, all those prefixes you learned about before can apply to these joules. So we can have kilojoules, millijoules, nanojoules, megajoules, all those things. Okay, another unit we have to know is something called a calorie. 1 calorie is going to be equal to 4.184 joules exactly. So sometimes when we talk about this heat energy, we talk in terms of calories. Sometimes we talk in terms of joules. We have to be able to convert between those. And this is the conversion factor. You need to know that conversion factor. Now, a thing to note, the calorie we're talking about here isn't the calorie that you see on the labels of food. Okay? That's a nutritional calorie. A nutritional calorie we're going to represent with a capital CAL instead of a lowercase cal, and 1 nutritional calorie is going to be equal to 1,000 regular calories, or 1 kilocalorie. So you need to know that conversion as well. Some other things we need to consider. We need to be able to identify a system, and we're going to identify whether a system is open or closed. We need to identify surroundings, and we need to identify a boundary. Okay, so let's look at the flask in this picture. And if I wanted to identify the system as being inside the flask, that's my system, and whatever liquid's in there, whatever's going on, that's my system. Because it's capped off, I'm going to call it a closed system. Now, it's not insulated properly, so it's not truly a closed system, but for the purposes of this picture, let's say it's a closed system. Okay, so inside the flask is my system. What's my surroundings? Well, that's everything outside the flask. What's the boundary? Well, the flask itself is the boundary. Okay, because it's not insulated, we can get transfer from the inside the flask, the system, to the surroundings. But no matter what energy we get transferred, remember, the overall change in energy, net change in energy, is going to be equal to the change in energy of the system plus change in the energy of the surroundings. Okay, that's the first law of thermodynamics. But we need to identify those 3 things when we consider thermodynamics and thermochemistry. All right, let's talk about these concepts a little bit more. So internal energy, if I look at an internal energy, delta E represents change in energy. That's going to represent E final minus E initial. Anytime you see that little delta symbol, it means final minus initial. Now, for a change in internal energy, let's look at something called an enthalpy diagram. If we look at the enthalpy diagram on the left, we can see that if we start with something at an initial state of a higher energy, going to a final state at a lower energy, what has to happen to go from that initial state to final state? Well, we have to give off energy. Where's that energy going to go? It's going to go to its surroundings. Okay, so as the initial state goes down, E final is going to be less than E initial. E final is a lower energy than E initial. So when I plug those values back into my delta E is going to be less than 0. Why? Well, because my final is a smaller value than my initial is. So if I have E final minus E initial, I'm going to end up with a negative value. Now let's look at the picture on the right. What if my initial state starts at a lower energy and I need to get it to a final state that's at higher energy? Well, how do I do that? Well, that means I have to put energy into the system. Where's that energy coming from? It's got to come from the surroundings. So now my E final is greater than my E initial, so my delta E is going to be greater than 0. It's going to be a positive value. All right, let's look at another example of this. So once again, delta E is equal to E final minus E initial. And keep in mind, any energy transferred from a system has to go to the surroundings. Any energy lost by the surroundings has to go to the system. Okay, we have to conserve that energy. Now also keep in mind, we can have a delta E, that change in energy is going to be equal to Q. Q is going to represent heat plus work, which is represented by W. So the heat and work lost and gained from the system and the surroundings, if we add those together, that's going to give us our overall delta E. All right, what does this mean? Well, let's look at the heat side first. We kind of already talked about this. So let's look at the picture on the left. If I start with hot water and I let it cool down, well, to go from that hot water to cool water, it has to lose heat. Where's that heat going? Well, it's going from that hot water into the surroundings. Okay, since I'm going from a higher energy to a lower energy, delta E is going to be less than 0. And that means I've lost heat. That Q is lost to the surroundings. So it's giving off heat. What if I start with ice water and want to get it to melted room temperature water? Well, if I start with ice water, that's at a lower temperature. If I go to that room temperature water, that's at a higher temperature. How do I get that? I have to put heat in. I have to heat that ice water up. Where's that heat coming from? It's coming from the surroundings. I'm going from a lower energy to a higher energy. Heat's going in, which means then my delta E is going to be greater than 0. Okay, so let's look at this with respect to work then. So I've still got those same two equations. Now with my work, in this case, I'm going to deal with the negative P delta V. So let's look at a picture of this. If I have zinc solid and aqueous HCl in my system, and that's hooked up to a piston, which has got an atmospheric pressure externally applied to it, well, that's my initial state. What happens as my zinc and HCl start to react? Well, they start to produce H2 gas. The H2 gas starts to create a pressure. Pressure pushes on the piston and overcomes that atmospheric pressure. Okay, so my initial state is at a higher energy than my final state. Since my initial energy is at a higher energy, I have to lose energy to go to my final energy. How am I losing that energy in this case? Well, I'm losing that energy because work is being done on that piston, which means work is being done on the surroundings. Okay, so in that case, I'm going from higher energy to lower energy. I'm losing work in the process. So keep these equations in mind. Now when we're dealing with work, we're going to look at a slightly different example. It's not always at negative P delta V. On the left, if we start with a fully charged battery and we put that wire attached to it, we can actually discharge the battery. And the wire will heat up and it'll produce that heat. And we'll lose that energy from the charged battery going to the discharged battery through heat. If I hook it up to a fan, now I'm going to lose the charge on the battery due to heat because I still have wires there. Passing that current through the wires is going to produce some heat. And I'm going to be doing work by spinning the fan. Now that's not the negative P delta V work, but it's still considered work because I'm moving that fan blade. Okay, so this is another example where we can see we can lose energy through heat. So we could just have delta E equal to Q, or we could have heat and work. We could have delta E equal to Q plus W. Okay, but this is going to introduce an important concept, and that concept is something called a state function. Right? What a state function means is it's something that's independent of the path it takes. Doesn't matter how you get from your initial state to your final state. All that matters is the difference between the initial state and the final state. So internal energy is a state function. If I take my octane and O2 as my initial state and I burn it, and I go to form CO2 and water as my final state, that energy difference is going to be the same whether I'm just burning that gasoline and lose all that energy as heat, or whether I'm putting that octane in a vehicle of some sort and losing energy in the form of heat and work. It doesn't matter in terms of the delta E. It doesn't matter which path I took. All it matters is what was my initial conditions, what was my final conditions. And that's going to be an important concept when we deal with something called enthalpy. So keep that in mind. That's what a state function is. It's independent of the path.